Okay, I'll pass to minima and maxima problem because you see here we don't need, now that we understand this, we don't need to do any numerical calculations because in order to write this, f will be given. This is capital F, okay, so all of these are capital F, okay, so this is capital F, this is capital F. Okay, so for this thing, f of x, y, z is given. P sub 0 as a numerical point is given. P is x, y, z. Okay? So write the equation or write an equation for the tangent plane of the surface given by f equals 0 at this point. All you have to do is calculate the gradient of this. Okay, so calculate gradient of f at p sub 0. So this is derivative of f at x sub 0. Put in x sub 0, y sub 0, z sub 0. And similarly with the others. Okay, so this is the only calculation you do in order to calculate the tangent, an equation for the tangent plane. Then you put it here. Well, you are done. If you are in the exam, this is enough. But normally, if you want to use this tangent plane for your own purposes, you can now simplify this and do whatever you like. Okay, so we don't need, I think we don't need numerical examples for this. There is no skill required. In some theories, we understand the theory, but the calculations are twisted, so you need to get used to it, but this is not one of those cases. So I'll skip numerical examples. I'll pass to the highlight of this chapter, minima, maxima problems. Okay? Okay, so min and max of functions of several variables. Okay, so we write this so that it is impressive, but we will concentrate on, so we will use two variables. The theory, as I explained, works for n variables, but the calculations involved are very complicated. Well, I use the word complicated in the sense that it takes time. Okay, so it's not it's not worth to do it in calculus, but in two variables the calculations are doable in a reasonable amount of time, meaning that we can ask questions in the midterm for this. Okay, so for this we need, so here we need some basic concepts from topology. So I'll mention these things. Topology is basically trying to understand which one is close, which point is close to which point without actually measuring the distance. Okay? Distance is something else. So we are talking about neighborhoods, but we will do this topology in Rn, in particular in R2. There is a distance there. So we will use this distance to define these concepts. The main thing that we are interested in is when you can move in any direction around a point. Okay, so this concept is explained by openness. So I'll start with this. So let's do this in R2, and you will see that everything works in R3, R5, etc. Okay, so let's do this in R2 first, and the second part is left as an exercise. Okay, so we have a point P sub 0, which is say x sub 0, y sub 0 in the plane. Okay, so the picture is like this. So this is always what you do. You start with very simple examples. You can draw pictures, you understand something, and you keep writing them, and then you forget about all the pictures and you look at what you have written. If it makes sense, now we have a theory. Okay, so here is the point P sub 0. Now we define this thing, B R P sub 0. We define this. Remember, this notation means that we are defining this. This is the set of all points P in R2 such that the distance between P and P sub 0 is strictly less than R. Here the important thing is I'm using strictly less than. Okay, so this is what makes this thing work. So it is, you see that it is open this, it's a disk like this. This radius is R. So these parts are the circumference. They are not included, but everything inside is included. Okay. So the name for this thing is open ball. Forget about what open means. This is just a name now. Open ball of radius R. R has to be always positive so that this thing will work. Okay, so you see this thing cannot be negative. Of radius R at P sub 0. Okay, so this is a name. Later on, right now we are going to make sense of this word. Okay. Now the nice thing about this open ball is that you always consider yourself at the center of this. You see that you can move in any direction you like. Why do we want this? We'll try to understand the derivative of the function at this point, for example. So the definition of derivative means that you can approach here without restricting the manner of approach. There is no curve, there is no pattern, okay? You just want to squeeze this towards P sub 0 and then you calculate the limit, okay? So all directions must be allowed for your function. So that's why this is our model for ideal calculations. But not all sets on which our functions are defined are like this, but they may locally be nice as these ones. So now we define what we mean by nice. Okay, a set say U in R2 is defined to be, so this is a name, defined to be open if at any point P sub 0 in U, we can find an open ball of radius R positive at P sub 0 such that this ball at P sub 0 totally lies in U. Okay? So wherever you stand on this set, all directions are allowed to you without exception. Okay? So these are nice sets for analysis. And in analysis, we call these things open sets. Okay? So example, first example, BR P sub 0 is an open set. That's why we called it open at the beginning, but when we called it open here, this was just an open ball, one name. Okay? But now that we have this concept of openness, this ball is open. Okay, let's look at the picture. This is P sub 0. This is radius R. So everything inside is allowed. This is my ball. Now choose any point here, P. Can I put a ball, open ball around this to lie totally in here? So from the picture it is clear. You can just stay away from, you can join this. You can join this to the origin. So if this is not on the circle here, if it is inside the disk, there is this positive distance. It is still away from the circle here. So take half of that distance. Okay, take this ball. You see that this is your new ball, and it totally lies inside here. Okay, so open balls are open sets. A counter example. Not open set. Okay, so let's again take a circle like this, but now here I put this part. Okay, so this picture. So this set is not open, okay, because you see here, if you take this shaded part, you can play this game, and for all those points, you can find a small radius so that the ball of radius r lies totally inside the set. But in this picture, the notation tells me that I also take this point as a point of the set. But here you see that this is just at the edge. No matter how small a ball I put here, there will always be points outside the set. Okay, so this condition is not satisfied for this set. Okay. Another good example. So this is not open. Consider R2. Okay, so here I said a subset of R2. R2 is a subset of itself. Okay, is it open? Take any point. Can you put an open ball around it so that the ball will lie in R2? Obvious, right? Take any radius you like. You can take a large disk around this point. Well, we are all living in R2, so this is trivially open. Okay. We will not be using this, but empty set is also considered an open set, but that's for mathematics department. When it's an empty set, we don't work on it. In calculus, we continue, but in topology, empty set is considered open. Okay, so if there is an open set, there must be a closed set. So let us look at the definition of a closed set. You see, we need these concepts because we will always be talking about an open neighborhood of a point. Okay, so that open should always mean that there is a ball around that. So that's why we are familiarizing ourselves with this concept. U in R2 is called closed if the complement of U is open. Okay, so anything outside, choose any point outside the set. You can find a small ball which is disjoint from the set. So all the points outside this set are away from this set. Okay, if you want to explain it in everyday language, you can always stay away from points of the set by an open ball. Okay, so example. Okay, so take this. Okay, so this is a closed set. Because take any point which is not on the set, you see that I can put a small ball here, disjoint from here. So the complement is trivially open. So this is closed. And R2 is closed since its complement is empty. Okay, but don't bother about this. This is a technical thing. Empty set is both open and both closed. R2 is both open and both closed, but these are just technical things. When you are working with R2, we will never work with empty set, so it doesn't matter. When you are working with all of R2, there is no problem. You can take any neighborhood you like. Okay, I'm giving it just as an example. And now I give the same example. So another example. I have this. Okay, so this is not closed. Okay, because you see these points, in looking at these mathematical concepts, you should always consider the extreme cases, because the concept tries to draw a line at the extreme cases. Now you see that these points on the circle here are not included in my set. This is the notation. But now, if you stand here and take, no matter how small an open ball around here, it is not disjoint from the set. It cuts the set. So points outside our set are not separated from our set. Okay, so it's not closed. You see that there are sets which are neither closed nor open. This set was not open and it is not closed. These sets exist. Okay, so in topology, unfortunately, we use the word open and closed, which in real life are opposites of each other, but in this sense they are not opposites of each other. Okay, so I was trying to avoid this thing, boundary. What is important to us will be the boundary. So these are the only three concepts I think we'll be needing. Open set, closed set, interior, exterior, boundary. So these are the only things. So a boundary, the boundary of, okay, so the boundary of U are those points in R2. So this is probably the only tricky thing in defining the boundary, because for closeness or for openness, we looked at the properties of the points in U or in U complement. But now I'm trying to understand something about U. All the points in R2 are candidates. Now I have a test. Whoever passes this test will be the boundary. Are those points on in R2 such that for any R positive, of course the interesting thing will be when you choose R smaller and smaller, the ball, the open ball, be those points say P in R such that I consider this ball around this, and of course to make things interesting, I'll choose R smaller, smaller, smaller. For all possible small R's, the ball intersects non-trivially. Non-trivially means that the intersection is non-empty, but of course if it is empty, then you will say why you are talking about it, but in mathematics department we talk about it. So if you want the intersection to be non-empty, we mention it. Okay, so this intersects non-trivially both U and U complement. You put a C here. This is complement of U in R2. Okay, so complement means all those points that are not in that set. Okay, so you see that now here, if I take this, the points here satisfy this condition, because no matter which open ball you choose here, there are points inside my set, there are points outside my set. These are boundary. Okay, so if I take this thing, I look at only the points inside. Again, the points here, you see that now this point does not belong to my set, but take any ball around it, it intersects the set, and it also intersects the complement of the set. So that's the boundary. So notation, we use this very often, so we give it a notation. Boundary of U is denoted by something like this. The reason why you use this notation, the same notation as differentiation, comes clear later on. I think we will not do this year, but if you look at the last chapter of the book, there is Stokes' theorem. And if you want to write Stokes' theorem in a very nice way so that you can remember, then this notation is very convenient. Okay, so that's why we chose this partial derivative notation for the boundary. Okay, so every time you face these words, think about the unit disk. The circle of the unit disk is the boundary of this. If you take out the boundary, what remains inside is the interior. Okay, and what remains outside of the unit disk, after you also consider the boundary, you take out the boundary again, that's the exterior. So these are the things that we will use. So let me also write this. So interior of U is U minus boundary of U. Okay, so this means set minus technically, and it means take away what you see on the right. Okay, so I don't care if U has a boundary or not. This says if U has a boundary, take out the boundary points. If U doesn't have a boundary, that's good. Okay, so what remains, we call it the interior of U. And similarly, exterior of U I don't think we'll use this very often, but we'll use this one. Exterior of U is, you look at the complement of this and take out the boundary of the complement. Okay, the same thing. So we will be using this thing. Again, why do we do this? If we have a set like this, and we will restrict our function here, we'll talk about its derivatives, then we don't want to talk about the derivative at this point. Okay? Because here you see I cannot approach to that point from these directions. They are outside my region of interest. So I take out those boundary points. What remains is open. Okay? So the whole idea of this technicality is we are trying to work on open sets. If the set is not open, we throw away those things that makes it not open. And what remains is open. You have a question?
The boundary of U and boundary of U complements is the same?
In topology, I hesitate to answer such questions because there are very extreme pathological cases. So I'll leave it to you as an exercise. So the boundary, yeah, one is tempted to say yes, but you have to think about this. Maybe there's a counterexample, but I'll check and I'll let you know. Okay, so this topology is very exciting. You have very exciting because you have these expectations. You write down something which looks very reasonable. It looks reasonable means that depending on your experience so far, this is what you expect. Okay, but your experience so far is not everything. Okay, so you learn it as you get older, so you hesitate. Okay, but basically that's what we expect. Normally you'll get counterexamples when there are you take out points from the set. Okay, so I don't want to enter into that. Okay, so this is open set. So why did we do this? Okay, so we'll look at minima and maxima. Okay, so this looks technical, but just think about the unit ball without the boundary. Okay, so now we have a function of two variables, z equals f of x, y. Okay, so this will also be true if we have a function of three variables, because I'll talk about neighborhoods of these things. Okay, so we say p sub 0. Okay, maybe I do this for a general case. We have a function f of p. Okay, we say p sub 0 is a local maximum for f if the following holds. Okay, so if there is an open ball Br p sub 0 such that f of p sub 0, so what did I say, maximum, greater than or equal to f of p for all p in this ball. Okay, so we will be doing this basically for 2 dimensions, so the picture will be something like this. Okay, if I take this r large enough, maybe the function here has a peak and then it goes up again at some other points, but here it has a peak. I'm trying to catch that peak, just like we did in one-dimensional case. In that case, instead of a ball, we said interval. Okay, in one-dimensional case, if you write the definition of an open ball, it will give you an open interval. Okay, if there's a small interval that this guy is the king on that village, then it's a local maximum. Okay, and it is called p sub 0 is a local minimum. So it is local here, local minimum for f if there is an open ball Br p sub 0 such that f of p is now small, less than or equal to f of p for all p in Br p sub 0. Okay, so our techniques will tell us how to catch these things. But just imagine the picture here. On top of this, there is a surface. If this is the peak Okay, the tangent plane there will be parallel to this surface, just like in one-dimensional case. The tangent line will be parallel to the x-axis. Here the tangent plane will be parallel to the xy plane. If it's a three-variable case, the tangent solid will be parallel to the xyz space, whatever that means. Okay, since it doesn't mean much in that case, so we have to use algebra. We have to look at partial derivatives. The partial derivatives must vanish. Okay, so this is, let me see what other terminology we must introduce before we continue to write down our basic result. Okay, so here the next thing is, of course, basic observation. Okay, so again, let's look at the two-dimensional case. We have a function of two variables. This is our xy plane. Okay, so there's a surface here. Suppose it has a local maximum here. Restricted to x-axis, or just, since this is just any point, draw a line parallel to x-axis. Look at the directional derivative in the direction of x, okay, or 0, 1. So this is the partial derivative with respect to x. So this gives you a curve on the surface. It has a maximum here. So the derivative must be 0. Okay, so the first partial derivative must be 0. Now do it the other direction. So you have another curve here. It has a maximum here. So the partial derivative with respect to y must be 0. All directional derivatives are 0, but who cares about the others? I can express any direction in terms of x and y. So I just take those two as fundamental. If p sub 0 is a local extreme point, local extreme point means that min or max, then gradient of f at that point is 0. Okay, so the 0 vector. In two dimensions, okay, if f is a function of, so if f is a function of x, y, this means, as we expect, f of x p sub 0 is 0, and fy p sub 0 is 0. So just like in the one-dimensional case, we call these things nice points. So these nice points will be called critical points. But again, experience tells us that if one of these partial derivatives does not exist, then at that point the function may have a minimum or maximum. Okay, so remember, in one-dimensional case, suppose we are talking about this curve like this. At this point, the derivative of the function does not exist, but it's a maximum. So these are also candidate. And the nature of this candidate, again, depends on the derivative. You try to calculate the derivative. It doesn't exist. So the derivative gave you an information about this point. So the information we derive from the derivative we call critical points. Okay? So these are our candidates in general. Okay? So if gradient of f at p sub 0 equals 0, okay, so if these hold, or one of the or if at least one of the partial derivatives do not exist at p sub 0, we call p sub 0 a critical point. So critical points are candidates to calculate local minima and local maxima. Okay, so calculus is again just like in one-dimensional case. We have these critical points. We calculate the value of the function at these critical points. If the domain of the function is everywhere, then these are our candidates. These numbers are candidates for minima and maxima. But we have to check if the function is going to plus or minus infinity. If there is a boundary, we have to check the values of the function at the boundary. We are carrying all the experience from one-dimensional case to two-dimensional case, except that the calculations here will take longer. Okay, the idea is the same. Okay, and we should have something corresponding to inflection point. In one-dimensional case, if you have a curve, the derivative may be 0 there, but then the function changes its mind and, okay, the function is increasing, the derivative is 0, but the function fools you and it continues to increase again. And that point is among the critical points, okay, but they are nice points. We call them inflection points. And there is a corresponding value here. We call them the saddle points, okay. So let me see if it is time to define this. Yeah, okay, so it's time to define this. So if P sub 0 is a critical point and, okay, so now the reason I stop here is because after you get busy with calculations, you check this end part and you find out that almost every point on the surface is a saddle point. I'm now defining saddle point. Okay, so the important thing is we are checking this condition only at critical points. Okay, so what is the basic description of a inflection point? Okay, at that point, the function has values smaller than this and the function has values larger than this. Okay, but take a straight line, take any point, this condition is satisfied. There are also always points smaller than this and larger than this, but they are not saddle points because that's not a critical point. The derivative is not 0 there. When the derivative is 0, we are trying to find out if it is minimum or maximum, and this guy comes and fools us. We call it a saddle point. Okay? If in every open ball B R P sub 0, there are points, say P1, P2 in the ball. They are different than P sub 0, such that f of P1 is less than or equal to f of P sub 0. This is less than or equal to f of P2. Okay. So this is where you expect the tangent line. We are working with nice functions, so the tangent line exists. The tangent line is parallel to the xy plane. But as you are approaching here, there is a direction where you approach here, and this thing looks like a maximum. And there is another direction where you approach. It is like this. Now it looks like minimum. Okay. So that's how you discover a saddle point, looking at how you approach to that point. Okay. So this is easy to visualize. You can look at the pictures of this. But in calculations, I'll come up with examples where something looks like a saddle point, but it will not be a critical point. Okay, so if the function is turning down and some of it is going down and some of it is going up, you expect that to be a saddle point. Okay, so sometimes it behaves like a saddle point, but it's not a critical point. Okay, so that will be an important example. Just keep in mind when I come there, I'll emphasize it. Okay, now. Okay, so now we can talk about the second derivative test. How you see, the reason I did these things for two variables is we have the second derivative test only for two variables. We have second derivative test for n variables, but the conditions to check take a long time, so we don't do that in calculus. But the idea works the same. So let me explain how second derivative test works in one variable. We'll do exactly the same in several variables. Okay, so how to decide if a critical point is a local minimum, local maximum, or a saddle point. So I have to finish this thing. Then P sub 0 is called a saddle point. Okay, so we have local maximum, local minimum, and saddle point. So how do we decide this? In one-dimensional case, in one variable case, remember we didn't do Taylor series, right? Anyway, there is this, so we'll do this later. We can write, in one-dimension case, we have mean value theorem. Well, extending the mean value theorem, we'll have this. Okay, f of x is equal to f of at x sub 0 plus f prime at x sub 0 times x minus x sub 0 plus f double prime evaluated at some mysterious point divided by 2 factorial x minus x sub 0 square for some c between x sub 0 and x. Okay, so this is the Taylor theorem, which we didn't do, but we'll do it. We'll do it this semester. Okay, so this is where the idea comes. You can approximate this function. You see, this is linear approximation. If you look at it this way, this is the equation of the tangent line to the curve y equals f of x at the point x sub 0. But when you use this instead of the function, you make an error, a small error. The error is precisely given by this, but of course we don't know where to choose. The theorem only says that there exists a point. There's definitely a point. If you can find that point and evaluate the second derivative there and write this is precisely the difference. So how do we use this? Normally, in the nice functions we are using sine or cosine. The second derivative is bounded. So we don't care where we will evaluate this. This number, absolute value, is always less than 1. So you see, if x is very close to x sub 0, its square is very small. So this is how we use this. Okay. Now the second derivative test means that this one, you see, this one is 0. The first is a critical point. So this is 0. You look at f of x minus f of x sub 0. So this is f double prime c over 2 factorial x minus x sub 0 square. Okay. If this is always positive, then this number is small. This is a local minimum. Okay. This will be always positive if this is always going to be positive. So you see that this part does not contribute anything. It's always positive. So we look at f double prime x sub 0. X is very close to x sub 0. If this is positive, and if f double prime is continuous, then it will remain positive in a neighborhood. No matter where you calculate it, it will always be positive. Okay? So if the second derivative is positive, then this thing will be positive. Then this is large, so this is local minimum. That's how second derivative test works in one-dimensional case. So in particular, when the second derivative is 0, it doesn't tell us anything about this, because this is the guy who's deciding. We are trying to predict its behavior by looking at the behavior of something we can calculate. But if this is 0, it doesn't say anything about this. So when you look at the second derivative test, it fails. Fails means that it doesn't make any claims when the value of the second derivative is 0. So in our case, it will be exactly the same. Okay. So our function of two variables will be written as the equation of the tangent plane at that point. And then at this point here, we will have an expression depending on the second derivatives. This time we have 3 second derivatives, actually 4, but we are assuming everything is continuous. So derivative with respect to x and y is the same as y and x. So we have 3 second derivatives, and somehow from them we get a criteria just like the positivity of this thing. When this is positive, this is minimum, it's a local minimum. So the expression we have there will tell us whether this is a local minimum or maximum. So that's what I'm going to write now. So maybe when I write it, we can stop, and next time we'll do lots of examples on this. In this case, we need to do examples. Okay, understanding the general theory just helps us to start the calculations, but doing calculations require some other skills than just the theory. Okay, so this is what happens in 2 dimensions. So this is my point, x sub 0, y sub 0. Take any point, okay, so for a local minimum, local maximum, I look at what's happening around this. So take any point here, okay, and consider this line. So suppose we go with x sub 0 plus h, y sub 0 plus k. Okay, h is delta x. Instead of writing delta x, I'm writing h and k. So here, h, k is a vector which is different than 0. 0, it just tells me in which direction I am moving. I'll consider all possible such vectors. You see that the important thing here is the ratio between them. Okay, so I will just look at the directions. So I'll take them small, okay, but they must define a direction, so I don't want 0, 0. 0, 0, I'll stay here. I restrict my function to this curve. So any point here, this is x sub 0 plus th, y sub 0 plus tk. Okay? When t is 0, we are here. When t is 1, we are here. Restrict the function to this line, f of x, y, to this line. Then there is only one parameter. Once I fix the direction, okay, so this is the just the fine point in these calculations. I'm doing this for all possible hk, but every time I consider a fixed hk. And I do a calculation, and I want to say something about the calculation which will hold no matter which hk I choose. Okay, so my official parameter is t. So I get a function of t. So this is f of x sub 0 plus th, y sub 0 plus tk. Okay. Now, if this function is, if the function has a minimum here, then it will have larger values here, but I'll use this one. Okay, I'll write this one. So the function at 1, okay, so this is the value of the function f, call this xy, f at xy, that corresponds to f of 1. So this is equal to, what does it say? I calculated at the center of my interest. This is f0 here. I'll write it later. Plus derivative at 0 times t minus 0 is t. Plus the second derivative calculated at some mysterious point, c between 0 and t. So at this point, I'll draw it there. 2 factorial times t square. Okay, so my x sub 0, my function is a function of t. So t sub 0 is 0. I'm just looking at t. Okay, for some c between 0 and t. So I evaluate the function here. This is x sub 0 plus ch, y sub 0 plus ck. Okay, so now I write what these are. Okay, so this is going to be 0, but okay, let's say f of x, y equals f of 0. You put t equals 0, so you have f of x sub 0, y sub 0 plus, I want to take the derivative of this with respect to t, so chain rule. Okay, so let me do it this way. Derivative of this with respect to x, evaluated at t equals 0, x sub 0, y sub 0, times h. Derivative of this with respect to t is h plus, I do the same thing with the second variable, times k. If it's a critical point, if this is a critical point, this will vanish, just like in the other case. Now the crucial part is what will come in terms of instead of this. Okay, so you take the second derivative of this. So in order to take the second derivative of this, maybe I write the first derivative at some place, then I'll take it. Okay, so here f prime t is equal to derivative of f, derivative of f respect to x at x sub 0 plus th y sub 0 plus tk times h plus, okay, do I have enough space there? Fy x sub 0 plus th y sub 0 plus tk. Okay. Now I'll take the derivative of this with respect to t. Okay. So it takes time, but we are not doing anything complicated. So let's start with this thing. Now I take the derivative of this with respect to t. Derivative of this function. This is my function. You see, this is the function, and later on this will be the function. So I take the derivative of this function with respect to x, evaluated at t equals 0, x sub 0, y sub 0, times h, plus I take this function, evaluated, take its derivative with respect to y, evaluated at t equals 0, I get this, and multiply it by k, okay? And I don't forget that there is an h here, so I multiply this with h. Plus, I do the same thing, so this whole thing is going to that. Okay, so let me do this, but I missed something here. Okay, so I'll do this. I'm not evaluating at t equals 0, I'm evaluating at t equals c. So it will take, okay, let me finish writing this, then we'll stop and I'll explain all this. So x sub 0 plus ch, because I have to evaluate this at a mysterious point. I don't know where it is. And y sub 0 plus ck times h plus f xy x sub 0 plus ch y sub 0 plus ck times k, and I don't forget that there is this h here, plus I'll do the same thing with this function. Now this is my function. I take its derivative with respect to x, evaluate it at this unknown point, times h plus f y ch y sub 0 plus ck k, and this whole thing was multiplied by k here, which I forgot. Okay, so it's k there, so I have k here. Okay, so this thing is equal precisely to this thing. Okay, if it's a critical point, these are 0. Okay, so these are equal to 0 if x sub 0, y sub 0 is a critical point. So this minus this, it will tell me whether this is minimum or maximum. The sign of this will depend on the sign of this. Okay, so on Thursday, we'll examine the sign of an expression like this. It has been explored since the time of Gauss. Everything is known about this. But I'll attempt to give a survey of this using only calculus. Okay, but I'll also give you the notation if you want to look at it in number theory books. We totally understand what happens to the signs of these things, no matter which HK you give to it. Okay, so that we will do on Thursday. Question? Huh? Yeah, t squared. Okay. Okay, thank you.